Tonight, we're going to explore one of the most unsettling possibilities ever to emerge from modern physics. Not because it predicts alien civilizations, hidden dimensions, or the fate of the universe, but because it suggests there may be infinitely many versions of you. Somewhere, there could be another you who made different choices, another you who never clicked on this video, another who became wildly successful, another who failed completely. And if some of the most respected theories in physics are correct, these aren't science fiction fantasies. They may be unavoidable consequences of the mathematics itself. What's remarkable is that this idea doesn't come from a single controversial theory. For nearly a century, 4 entirely separate branches of physics have been developing along their own paths. Number 1, cosmic inflation, born from the study of the early universe. Number 2, quantum mechanics, traced back to a 1957 thesis written by a young physicist named Hugh Everett III at Princeton under the guidance of John Wheeler. Number 3, string theory, built from the mathematics of vibrating dimensions. And number 4, holography, born from the geometry of black holes. 4 different fields, 4 different research traditions, 4 different sets of equations. And yet, when each of them is followed to its conclusion, they arrive at the same astonishing answer. Our universe is almost certainly not the only one. The multiverse is not a speculation added on top. It is a mathematical output these theories produce, whether physicists want it or not. By the end of tonight, you're going to understand why each of these 4 branches independently points toward other universes, how the convergence of inflation, quantum mechanics, string theory, and holography reshape the question, and what it means that the multiverse may be a serious scientific conclusion rather than a philosophical guess. And there's one implication near the end of this story that completely changes how most people think about existence itself. So stay with me. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why the multiverse became a serious scientific hypothesis, you have to start with a problem physicists did not go looking for. It found them. The universe runs on a set of physical constants, numbers baked into nature itself, the strength of gravity, the force that holds atoms together, the energy threaded through empty space. These numbers were not derived from deeper principles. They were measured. And when physicists looked carefully at those measurements, they found something they could not explain. The numbers are precise in a way that seems almost impossible to account for. Here's what the measurements actually show. Gravity must fall within an extraordinarily narrow range for stars to exist at all. Change its strength by 1 part in 100 million, and the consequences are catastrophic in either direction. Too strong, and stars burn out in thousands of years, far too short a window for planets to form or chemistry to develop. Too weak, and hydrogen never clumps together in the first place. Stars simply don't ignite. Either way, the universe stays dark. 1 part in 100 million is not a large margin. It is a razor's edge. The ratio between electromagnetism and the strong nuclear force, the force that binds atomic nuclei together, is equally unforgiving. Shift that ratio by a few percent and atoms cannot form. No atoms means no molecules means no chemistry, no water, no carbon. The entire periodic table evaporates as a possibility. And then there is the cosmological constant. This is the energy of empty space itself, a number that governs how fast the universe expands. The measured value is tuned to 1 part in 10 to the power of 120. To write that number out, you would write a 1 followed by 120 zeros. That is not a rounding error. That is not a small adjustment within a reasonable range. Think of it this way. If you took every atom in the observable universe and tried to represent each one with a single decimal place of precision, you would still fall short by dozens of orders of magnitude. 1 part in 10 to the power of 120 is finer than anything in nature we have a comparison for. Physicists called it the worst prediction in the history of science. Not because the measurement was bad, because the precision required to land on it by accident is so extreme it borders on absurdity. So physicists found themselves facing a question they could not dismiss. Why these numbers? Why not slightly different ones? Why not dramatically different ones? The universe did not have to produce stars or carbon or chemistry. The vast majority of possible number combinations produce a universe that collapses within moments of forming or expands so fast that matter never gathers into anything at all. The window where complex structure can exist, where elements heavier than hydrogen can form, where life becomes possible, is extraordinarily small compared to the space of what was theoretically available. Two explanations were on the table. The first was design. Something or someone set the dials deliberately. This is an answer, but it is not a physics answer. It places the explanation outside the reach of equations and testable models. Science cannot work with it. The second explanation was stranger and, to many physicists, more troubling. What if there are vastly many universes, each with different values for these constants, and we simply find ourselves in one of the rare ones where the numbers permit us to exist? Not because ours was chosen, not because it was inevitable, but because the others, the overwhelming majority, produce nothing capable of asking the question. This is the multiverse, not as a mystical claim, as a cold mathematical accounting. If enough universes exist with enough variation in their constants, the odds that at least one lands in the habitable range stop being shocking. We would be the statistical outlier that happened to work. This argument does not prove the multiverse. It does not give us an address for another universe or a way to detect one. But it transforms the multiverse from a philosophical fantasy into a scientific question. It gives physics a reason to ask whether the multiverse is real rather than simply dismiss it. But the reality was different. The fine-tuning argument was not invented in response to a crisis. It was noticed gradually as the measurements got more precise, as the tolerances got narrower, as physicists realized the numbers were not just convenient, but almost impossibly so. The argument for the multiverse had already been developing for decades before the cosmological constant delivered its most extreme version of the problem. In 1957, a graduate student at Princeton University submitted a doctoral thesis. His name was Hugh Everett III. His argument was not about fine-tuning at all. It was about quantum mechanics, the theory governing the behavior of particles at the smallest scales. And his thesis proposed something that the physics community was not prepared to hear. Every quantum event, Everett argued, does not simply produce one outcome. Reality itself splits. Every possible outcome occurs, each one in a separate, equally real branch of the universe. What we observe is not nature choosing between possibilities. It is us finding ourselves in one branch while the others continue alongside us, forever inaccessible, but genuinely real. His advisor was John Wheeler, the same John Wheeler who would later coin the term black hole. Wheeler told Everett the idea was too radical. He asked him to tone it down. Everett refused. The thesis was published in a condensed form. Everett left academic physics shortly after. For years, the idea was treated as an interesting thought experiment at best, a curiosity at worst. That was not the end of it. Decades passed. The mathematics of quantum mechanics kept developing. Physicists kept running into the same problem Everett had tried to solve. The equations of quantum mechanics, followed to their logical conclusion, do not naturally produce a single outcome. They produce a superposition of all outcomes simultaneously. To get a single result, theorists had to add something extra, an intervention, a collapse of the wave function, a process that had no good physical explanation. The math kept pointing somewhere uncomfortable. What was once considered too radical is now, among many physicists, considered the most mathematically consistent account of quantum mechanics available. Not universally accepted. Still debated, but no longer dismissed. The physics world did not grow less radical on this question. It grew more radical, and Everett's work was only one door. Since 1957, separate branches of physics working on completely unrelated problems have followed their own equations to their own conclusions. not looking for the multiverse, not trying to explain fine-tuning, simply following the mathematics, and each of them has arrived at the same answer. The multiverse does not appear in these theories because someone wanted it to. It appears because the equations produce it. Remove it, and the math breaks down. Keep it, and the math holds together. 4 different sets of equations, 4 different research traditions, 1 conclusion. Think about what that means. 4 doors, each open from a different direction, each leading into the same room. That kind of convergence across independent research programs that had no contact with one another is not something physics dismisses easily. And the details of what each door reveals are far stranger than the fine-tuning argument alone ever suggested. Let's begin with the first of those doors, and with a young physicist sitting with 3 problems no one had solved. The year was 1979. Alan Guth was at Cornell, and the standard Big Bang model was, by any measure, a triumph. It explained the universe's expansion. It predicted the abundance of hydrogen and helium in the cosmos. It accounted for the faint glow of radiation left over from the early universe, the cosmic microwave background. These were genuine, remarkable achievements. But 3 things refused to fit. The first was called the horizon problem. Look in opposite directions across the observable universe, and the 2 regions you're looking at are separated by roughly 93 billion light years. They have never been in contact. No signal, no light, no information of any kind has ever passed between them. The universe simply hasn't been old enough for that to happen. And yet, when you measure the temperature of the radiation coming from both directions, they match. Not approximately. Not within a few percent. They match to within 1 part in 100,000. The same temperature to extraordinary precision in regions that should have no knowledge of each other whatsoever. That is the horizon problem. The second was the flatness problem. Space, when measured carefully, is flat. Not curved like the surface of a sphere. Not saddle-shaped. Flat. And flatness in cosmology is deeply unstable. Think of a pencil balanced perfectly on its tip. Leave it alone for a fraction of a second and it falls. A universe that is even slightly curved will diverge from flatness rapidly as it expands. For space to measure as flat today, it would have had to be flat at the moment of the Big Bang, to within 1 part in 10, to the power of 62. That is a decimal point followed by 62 zeros before you reach the first significant digit. The slightest deviation in either direction, and the universe would have either collapsed back on itself within seconds, or expanded so fast that matter never gathered into anything at all. Here's what scientists believed at the time. This extraordinary precision was simply a given, a feature of the initial conditions, unexplained. The third was the monopole problem. Grand unified theories, the leading framework for unifying the forces of nature, predicted that the early universe should have been flooded with magnetic monopoles. A monopole is a magnetic particle with only 1 pole, either north or south, with no counterpart. The theories predicted they should be everywhere. They have never been detected. Not 1, 3 problems. Unrelated, in every outward sense. And Guth solved all 3 with a single idea. Inflation. In the first roughly 1/10 trillionth of a trillionth of a trillionth of a second after the Big Bang, a time so brief it barely registers as time at all, the universe underwent exponential expansion faster than light. A region of space smaller than a proton expanded to roughly the size of a grapefruit in that fraction of a second. Then inflation stopped, and normal expansion took over. That sounds almost impossibly fast, and it was. But the consequences were clean. Before inflation stretched space apart, everything in the early universe had been in contact, in equilibrium, at the same temperature. Inflation then pushed those regions apart faster than light could cross between them, which is why opposite ends of the sky look identical today. They start that way. Inflation also explains flatness. Blowing up a balloon, any balloon, flattens its surface. The more you inflate it, the flatter any small patch of it becomes. A universe that inflated by the extraordinary factor inflation requires would have any initial curvature smoothed to undetectable levels. And monopoles. If inflation diluted the early universe by that same factor, the density of monopoles would drop to roughly 1 per observable universe. We wouldn't expect to find one, we haven't. 1 mechanism, 3 problems. Gone. And then inflation made a prediction. If the universe underwent this rapid early expansion, the quantum fluctuations present during inflation would have been stretched across the sky, leaving a specific pattern of temperature variations in the cosmic microwave background. Not random, not uniform, a specific, calculable pattern. In 2003, NASA's WMAP satellite mapped those fluctuations with precision. The pattern matched. In 2013, the Planck satellite refined that map further. The pattern still matched. Inflation is now the leading cosmological model. It was not forced on the data. The data reached for it. But here's where it gets strange. The mathematics of inflation does not want to stop. The mechanism at the heart of it, what physicists call the inflaton field, is a form of energy that drives exponential expansion. When the inflaton field decays in a given region of space, inflation ends there, and a Big Bang-like event seeds a universe like ours. But the field doesn't decay everywhere at once. It decays in patches, randomly. In one region, inflation ends. In the surrounding regions, it keeps going. Those regions expand faster than the patch that stopped. New patches form and stop. New regions keep going. The process never terminates. There is always more inflating space than stopped space. Always more patches forming than have formed. This is eternal inflation. It was not the goal. No one designed it in. It emerged from the mathematics whether anyone wanted it or not. The result is a level 2 multiverse, an ever-expanding foam of causally isolated bubble universes. Each bubble where inflation ended is, in principle, a universe. Each is causally separated from the others. The bubbles cannot communicate. We cannot reach them. We cannot signal them. We cannot observe them directly. But they are not a philosophical flourish. They are the inevitable output of the same mathematics that correctly predicted the pattern of fluctuations in our own sky. And this is where André Linde enters the story. Linde was not a peripheral figure. He developed the most complete and mathematically rigorous models of inflation available. He understood the theory from the inside. And he spent years trying to find a version of inflation that does not produce a multiverse. A version where the inflaton field decays uniformly everywhere. A version where inflation simply ends. He could not find one. Not because he stopped looking. Not because the question was intractable. But because the multiverse is intrinsic to the mathematics of inflation itself. Remove it, and inflation breaks. Keep it, and inflation works. And inflation works in ways we can measure. Now consider what follows from the bubble structure. In each bubble where inflation ends, the physical constants that emerge can, in principle, differ. The mass of the electron, the strength of the electromagnetic force, the value of the cosmological constant. These are not fixed by inflation itself. They are determined by how the inflaton field settles, and that settling can vary from bubble to bubble. Most bubbles, by any reasonable accounting, would land on values that produce nothing. No atoms, no stable chemistry, no possibility of the conditions that allowed us to exist. A handful, across an effectively infinite foam, would land close enough to the values we measure. This brings everything back to where this conversation began. The fine-tuning problem asked why the constants are what they are. The multiverse answers with the law of large numbers applied to physics. If there are enough bubbles with enough variation, the habitable ones will exist. We are in one of them because we could not be in any other. Inflation, the best explanation of our own universe's earliest moments, carries the multiverse inside it whether we invite it or not. One door opened, one conclusion followed, and this was only the first door. Now, leave the foam of universes behind for a moment. Set aside the vast, silent bubbles drifting apart through an ever-expanding inflation that never ends. The second door to the multiverse is not found by going further out. It is found by going further in. down past the scale of cells, past the scale of atoms, to the smallest events that physics can describe. A single particle, a single moment, a single measurement. This is where the second door opens. In the mid-1920s, 3 physicists built a framework that would change everything. Niels Bohr, Werner Heisenberg, Erwin Schrödinger. What they produced was quantum mechanics, and in the century since, it has become the most precisely tested theory in the history of science. Its predictions match experiment to 1 part in a trillion, not approximately, not in most cases, to 1 part in a trillion across every test ever devised. No other theory in physics comes close to that record. And yet quantum mechanics contains, at its very core, something it cannot explain. Here is what scientists had to confront as they developed the theory. Before you measure a particle, it does not have a definite position, not an unknown position, not a position you simply haven't found yet, a genuinely indefinite one. The particle exists in a superposition, a state that contains all possible outcomes simultaneously. The position is not hidden from you. It does not exist until the moment of measurement. Think of it this way. Imagine a coin suspended in the air, spinning, but not a real coin, with a real face hidden as it tumbles. A coin with no face at all until the moment it lands. Before measurement, there is no heads, there is no tails, there is only the superposition of both. Then you look, and one outcome appears. Physicists call this collapse. The wave function, which had spread across all possibilities, collapses to a single outcome at the moment of measurement. The other possibilities vanish. One result remains, but something was wrong. Nothing in the mathematics of quantum mechanics actually causes this collapse. This is the central crack in the foundation. The equations of quantum mechanics are deterministic. They evolve the wave function smoothly and continuously. They produce superposition. They spread possibilities. They never, on their own, produce collapse. Collapse was not derived. It was not predicted. It was added by hand, bolted onto the theory, because without it the math would say that particles never have definite properties. Ever. This became known as the measurement problem. And the most widely taught resolution of the measurement problem is what is called the Copenhagen interpretation. Bohr's answer was essentially this: collapse happens at measurement, and asking what causes it is not a meaningful question. The wave function is a tool for making predictions. When you measure, it collapses. Do not ask for more. That answer has held for decades, but it leaves several questions with no answer. What counts as a measurement? Does the collapse require a conscious observer? Does it require a detector? Does it require a machine of a certain size? At what scale does quantum behavior become classical behavior? At 1 atom, the quantum rules apply. At a table, they clearly do not. But at what threshold does the transition happen? The Copenhagen interpretation does not say. It cannot say. These questions have no answer within that framework. In 1957, a 27-year-old doctoral student at Princeton named Hugh Everett III decided to try something different. His proposal was simple and, at the time, almost entirely dismissed. Take the equations literally. Remove the collapse postulate entirely. Do not add the hand patch. Do not declare that measurement triggers a special physical process. Just follow the mathematics wherever it leads. What does the mathematics say? If a particle is in superposition before measurement and a detector interacts with it, the detector does not collapse the wave function. The detector enters superposition too. Both outcomes persist. The detector that read spin up and the detector that reads spin down both exist, encoded in the same evolving wave function. Then the scientist reads the detector. The scientist enters superposition. Then the room. Then the building. Then the planet. An ever-growing entanglement of possibilities. Never collapsed, never reduced, simply branching. With each branch carrying a complete and internally consistent version of events. We experience only one outcome, because we are inside one branch of that superposition. The scientist who measured spin up is in one branch. The scientist who measured spin down is in another. Neither can see the other. Each experiences a single definite result. Each believes collapse happened. Neither is wrong from inside their branch. But no collapse occurred. The wave function simply grew. This is the many worlds interpretation. Not Everett's name for it. His name was the relative state formulation. But many worlds is what it became, and that name, while vivid, carries a misleading connotation of extravagance. Wait. Many worlds is not the extravagant interpretation. It is the parsimonious one. Consider what the Copenhagen interpretation requires. It requires an additional physical process, collapse, with no mechanism, no equation governing it, and no specification of when or why it occurs. It requires that observation play a special role in physics without explaining what makes observation special. It requires that quantum mechanics and classical mechanics operate by different rules at different scales without defining the boundary between them. Every one of those requirements is an assumption added to the base mathematics. Everett's interpretation requires none of them. No collapse mechanism, no special role for observation, no unexplained transition from quantum to classical. The wave function evolves. That is all. Many worlds is not the interpretation that adds the most. It is the interpretation that removes the most. The one with the fewest extra assumptions. The simplest reading of the equations, not the most dramatic one. Branching does not divide reality the way splitting a cake divides a cake. The cake has a fixed amount of substance, and cutting it produces smaller pieces. Branching is closer to copying a document. Each copy is complete. Each copy is whole. Nothing is reduced. The wave function grows with each branching event, and every branch it produces is a full, internally consistent world. Now think about the rate at which this occurs. Quantum events happen trillions of times per second in every cubic centimeter of matter. Not occasionally. Not in laboratories only. In the air around you, in the atoms of your body, in the molecules that make up every surface you can see. Branching is not rare and dramatic. It is continuous and relentless. It has been continuous since the Big Bang. Every quantum event, every particle interaction, every radioactive decay, every photon absorbed by a molecule, each one a branch point, each one splitting a world. The implications are difficult to hold. At this moment, there is a version of you that followed every word in this section without difficulty. There is a version that lost the thread 2 minutes ago and is still here. There is a version that closed the video before this section began, and branching extends in every direction through time. There are branches where the asteroid that struck the Earth 66 million years ago arrived at a slightly different angle. Branches where it missed entirely. Branches where every significant event in your life, and in the lives of everyone who came before you, went differently. Extending back through every quantum event in the history of matter. The number of branches is not merely large, it is effectively infinite. And in the mathematical framework of quantum mechanics, each branch is equally real. Not metaphorically real, not approximately real. Real in the same sense that the branch you are currently inhabiting is real. Quantum mechanics did not predict this because anyone wanted it. It emerged from taking the most precisely tested theory in the history of science and asking what its equations actually say. The answer, when you follow the logic without flinching, is that every possible outcome of every quantum event becomes its own branch of reality. The measurement problem is not a mystery in need of a patch. It is a door, and the second door has now opened. 2 independent branches of physics, developed by different people, for different reasons, following entirely different mathematical structures, have now arrived at the same place. The question is whether the third and fourth agree. Let's set that picture aside for now. 2 doors have opened. 2 independent branches of physics, developed by different people, working on entirely different problems, have each arrived at the same conclusion. But the third door comes from somewhere unexpected. It comes from a problem physicists have been carrying since the 1920s. And the problem is this: the 2 most successful theories ever constructed refuse to fit together. Quantum mechanics describes the very small, Particles, atoms, energy, the behavior of matter at the tiniest scales. It is astonishingly accurate. You have seen that already. And general relativity describes the very large, gravity, space-time, the curvature of the universe, the behavior of matter at the largest scales. It is also astonishingly accurate. GPS satellites require relativistic corrections to function. The gravitational waves detected in 2015 matched Einstein's predictions from a century earlier almost exactly. These two theories together account for essentially everything we can observe in the physical world. But here's the problem. They are mutually incompatible, not in their predictions, where they operate on different scales and rarely compete. Incompatible in their mathematical foundations. Quantum field theory, the precise form that quantum mechanics takes when applied to particles and forces, treats particles as points. Infinitely small, dimensionless points. General relativity treats space-time as a smooth, continuous fabric that bends and curves according to mass and energy. When you try to combine these two pictures, when you try to describe what happens at a scale small enough that both theories should apply simultaneously, the mathematics breaks. You ask a simple question. What is the energy of empty space at the quantum scale? And the equation gives back infinity. Not a large number. Infinity. Infinities appearing in the answer to a physical question are a sign the theory has broken down, that something deeper is missing. Physicists spent decades searching for what was missing. In the 1970s and into the 1980s, a new proposal emerged. It was radical, technically demanding, and unlike anything that had come before. The proposal was string theory, and its core idea was simple to state, even if the mathematics behind it took years to fully develop. Particles are not points. They are tiny, one-dimensional vibrating strings. Think of each fundamental particle not as a dot, but as an incredibly small loop or strand, far smaller than any scale current technology can probe, oscillating in a particular pattern. Different vibrational modes produce different particles. A string vibrating one way becomes an electron. Vibrating another way, it becomes a quark. Vibrating in yet another mode, it becomes a hypothetical particle called the graviton, the quantum carrier of gravity, which quantum field theory had never been able to accommodate without producing infinities. Everything from one object. All particles, all forces, all the diversity of matter emerging from a single fundamental entity in different states of vibration. String theory passed every internal consistency test physicists threw at it. Where quantum field theory generated infinities when gravity was included, string theory remained finite. It resolved the infinities not by patching them over, but by removing the conditions that caused them. It naturally incorporated gravity. It did not require gravity to be added as an afterthought. Gravity was already there, built into the mathematics. Through the 1980s and into the 1990s, string theory was the leading candidate for what physicists called a theory of everything, a single framework from which all physical laws would follow. But string theory carried a requirement, and the requirement was strange. For the mathematics of string theory to remain consistent, space cannot have 3 dimensions. The original formulations required 10 spatial and temporal dimensions in total, or in some versions 11. 10 or 11 dimensions of space-time, where we experience only 4. The others must exist. The mathematics demanded it. But they must be hidden, curled up, compactified, folded into structures so small that no current particle accelerator could detect them. Picture a long, thin garden hose viewed from a great distance. From far away, it looks like a one-dimensional line, but up close it has a second dimension, a circle running around its circumference, too small to see unless you are close enough. The extra dimensions of string theory work on a similar principle. They are real. They are present in every point of space. They are simply too small to observe directly. This was already an extraordinary claim. Extra dimensions curled up below the threshold of detection. But string theorists accepted it because the mathematics required it, and the mathematics produced a theory that was otherwise self-consistent and more complete than anything that had come before. So the question became, how exactly do these extra dimensions curl up? And here is where everything changed. When physicists calculated the number of ways the extra dimensions could be arranged, the number of distinct geometric configurations that satisfied all of string theory's consistency conditions, they found not one answer. Not 10, not 1,000, not 1,000,000. Approximately 10 to the power of 500 distinct solutions. 10 raised to the 500th power. To give that number even approximate meaning, the total number of atoms in the observable universe is roughly 10 to the 80. The number of all possible quantum states in the observable universe, by some estimates, does not reach 10 to the 120. 10 to the 500 is not just larger. It is so much larger that no comparison to physical quantities in our universe gives it adequate scale. It is a number so vast that if every atom in the observable universe were itself an observable universe, and you counted all the atoms in all of those, you would not be close to 10 to the 500. This was not what string theorists wanted. They were searching for uniqueness. A theory of everything should produce one answer, one set of physical laws, one explanation for why the electron has the mass it has, why gravity is as strong as it is, why the cosmological constant is what it is. Instead, they found a landscape. Physicists began calling it exactly that, the string landscape. A vast terrain of approximately 10 to the 500 possible configurations, each one corresponding to a distinct arrangement of the extra dimensions, and each arrangement producing different physical constants, different electron mass, different gravitational strength, different cosmological constant, different particle content, different physics, not slightly different, completely different, most of them incompatible with atoms, stars, or anything resembling structure. The landscape did not predict our universe. It predicted an enormous set of possible universes, of which ours was one. But here is where the third door connects to the second. You will remember the bubble universes from eternal inflation. In eternal inflation, the inflaton field decays in patches, producing an ever-expanding foam of causally isolated regions. Each bubble forms with its own physical properties, depending on how the field settles in that region. Now consider the string landscape alongside eternal inflation. If the extra dimensions of string theory can curl up in 10 to the 500 distinct ways, and if bubble universes in eternal inflation can each settle into different configurations of those dimensions, then each bubble does not just have different field values. Each bubble can inherit a different point on the string landscape. Each bubble can have fundamentally different physics. The two theories do not merely coexist, they reinforce each other. Eternal inflation provides the mechanism, the string landscape provides the menu. Together they produce a multiverse that is not merely vast, but comprehensively varied. Every configuration the mathematics permits, realized somewhere in the foam. Leonard Susskind, one of the founders of string theory, spent years resistant to this conclusion. But in the early 2000s, he came to argue that the landscape was not a failure of string theory. It was the explanation physicists had been missing. If there are 10 to the 500 possible configurations of physical laws, and if eternal inflation realizes all of them somewhere, then the question of why our constants are what they are has an answer. Not a unique answer derived from first principles. A sampling answer. We observe the constants we do because we exist in a region where the constants permitted our existence. Most configurations produce no atoms, no chemistry, no observers. The ones that do are the only ones in which anyone asks why. This is the anthropic principle, applied at cosmological scale. Not a universe uniquely designed for life. A universe that appears designed because we can only observe from within a life-permitting configuration. Serious physicists, including some who accept eternal inflation and take string theory seriously, find this uncomfortable. The objection is pointed. A theory that admits 10 to the 500 solutions can, in principle, accommodate almost any observation after the fact. You cannot use it to predict. You can only use it to explain, and explaining everything explains nothing. That objection is genuine. It does not go away, and it will return. But string theory's defenders reply with equal force. The landscape was not chosen. It was not inserted to make the multiverse work. It emerged from the only mathematics that successfully unifies quantum mechanics and gravity. The math produced it. One cannot simply ignore what the mathematics says because the answer is uncomfortable. The third door did not open because anyone searched for a multiverse. It opened because physicists followed the only complete unification of the two most powerful theories in science, followed it to its logical conclusion, and found 10 to the 500 roads diverging in the dark. And the fourth door has not yet opened. The fourth door came from outside physics entirely. It came from a philosopher, and for years that was a reason enough to dismiss it. But the dismissal did not hold. In 2003, Nick Bostrom published what he called the simulation argument. The logic was precise, and it took the form of a trilemma. One of three statements must be true. Either civilizations almost always destroy themselves before they ever achieve the computational power needed to simulate detailed, conscious histories of the past, or civilizations that reach that threshold almost always choose not to run such simulations, or we are almost certainly living inside one right now. Those are the only options. Bostrom did not claim to know which one was true. He pointed out what follows if the first two are false. If civilizations do survive to that threshold, and if even a small fraction of them run historical simulations, the number of simulated minds would vastly outnumber the minds in base reality. Not by a little, by an astronomical margin. Any conscious observer, drawn at random from all conscious observers that have ever existed, would be statistically far more likely to be simulated than real. The argument does not require certainty, it requires only probability. Philosophers argued about it, physicists largely ignored it, and then they stopped ignoring it. Here is what made them look again. The universe, at its deepest level, is not continuous. It is discrete. Think about what physics actually finds when it looks at the fabric of reality at the smallest possible scales. At roughly 10 to the negative 35 meters, the Planck scale, space itself becomes granular. Not smooth, not flowing, grainy and undefined, like an image on a screen when you press your face too close and the individual pixels become visible. Below that scale, the smooth geometry of general relativity breaks down entirely. Quantum mechanics and general relativity, the two pillars of modern physics, stop agreeing before they reach that point, and what lies beneath is undefined. What we do know is that at every level above it, the physical world is quantized. Energy does not come in continuous streams. It comes in packets, quanta, the smallest indivisible units. Particle properties like spin and electric charge do not vary smoothly across a continuous range. They are fixed, discrete values, not a dial, a set of switches. That is what the equations say. The answer was stranger than expected. It is also exactly what you would expect if the universe were running on finite computational hardware. Think about why. A continuous simulation is infinitely expensive. To represent a perfectly smooth, infinite resolution reality on any physical machine, you would need infinite memory, infinite processing power. No real computational substrate could do it. But a discrete simulation, one built on a grid with a smallest unit of length and a smallest unit of energy, is computable, finite, tractable. The universe looks, at its foundations, like what the constraints of finite hardware would produce. That observation remained speculative until 2012. Then Silas Bean, leading a research team at the University of Washington, asked a more precise question. If our universe were running on a discrete lattice, a grid with a specific resolution, would it leave any observable signature in the data? It would. A lattice has a finite resolution. That resolution would impose a maximum on the energy any particle could carry. Just as a digital image has a maximum frequency, it can represent before the sampling breaks down. A simulated lattice would cap the energy of particles propagating through it. Cosmic rays, high-energy particles that reach us from across the universe, would hit that ceiling. Above a certain energy, they would simply stop. The Greisen-Satzepin-Kuzmin cutoff, known as the GZK cutoff, is exactly such a ceiling. It is a maximum energy for cosmic rays, observed experimentally. It has a standard explanation in conventional physics: interactions between cosmic rays and the cosmic microwave background radiation as they travel across vast distances. That explanation was established before Bean's team published their work. The GZK cutoff is not mysterious. It fits within ordinary physics. But it is also consistent with the simulation hypothesis. The signature that a discrete computational lattice should produce already exists in the data. The simulation hypothesis predicted it, and it is there. This does not prove simulation. That distinction matters. What it does is something more precise. The philosopher Karl Popper argued that hypothesis becomes scientific not by being proven, but by being testable. A hypothesis that could in principle be proven wrong by an experiment is a scientific hypothesis. One that cannot be is not. The simulation argument, for most of its life, had no testable predictions. It was philosophy. Then Bean's team identified a class of observable signatures that a simulated universe should have and a base reality universe should not. The hypothesis became, in principle, distinguishable from its alternative. Not proven, not disproven, testable. That is what moves an idea from speculation into science. Most physicists remain skeptical. The specific claim that we are living inside a computation faces enormous unresolved difficulties. How would a computational substrate outside our universe work? What would it be made of? How do you test the difference between the GZK cutoff as a lattice artifact versus the GZK cutoff as standard high-energy physics? Those questions are genuinely open, and they are hard. The skepticism is not dismissal. It is appropriate scientific caution. But the broader implication does not depend on whether the simulation hypothesis is true. It depends only on whether it is coherent enough to ask. If our universe could in principle be a simulation, it is, by definition, embedded within a larger substrate. That substrate exists outside our universe. It may be running other simulations in parallel, other universes with different initial conditions, different physical constants, different histories. The multiverse that emerges from the simulation argument is not made of quantum branches, or bubble universes, or string vacua. It is made of other computations running alongside ours on the same hardware. 4 doors. 4 entirely different approaches. Fine-tuning and the mathematics of inflation. The unresolved equations of quantum mechanics. The string landscape and the geometry of extra dimensions. And now, a philosopher's logical trilemma, given teeth by a lattice signature that was already sitting in the cosmic ray data. Each door was opened by different people, working in different fields, following different problems. Each one leads into the same room. That convergence is not nothing. And there is more to say about what it means. There is more to say. And some of it is already written in the sky. Physics is empirical. The theories we have been tracing through these 4 doors are only as good as what the data says. And the question worth asking, carefully, is whether the sky already contains anything that points in this direction. Not proof, not confirmation, but something measurable, something anomalous, something that does not fit cleanly into the standard picture. It turns out the sky has 2 things to say. The first comes from the large-scale motion of galaxy clusters. A galaxy cluster is not a single galaxy. It is a structure containing hundreds or thousands of galaxies, bound together by gravity, spread across millions of light years. These are the largest coherent objects in the universe. And in 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center announced something that did not fit the models. Here is what scientists believed at the time. On the very largest scales, the universe is roughly uniform. Matter is distributed without a preferred direction. The motions of distant galaxy clusters, after accounting for local gravitational influences, should be essentially random. No net drift, no shared direction. Just the statistical noise of a cosmos that has no center and no edge, pulling harder than any other. That was the expectation. But Kashlinski's team found something else. Studying the motion of galaxy clusters spread across billions of light years, they found that the clusters were not moving randomly. They were moving consistently, coherently, in one direction. Not a small sample, not a local region. Clusters across an enormous stretch of the observable universe, all drifting together. They called it the dark flow. The critical point is this. The dark flow could not be explained by any known structure inside the observable universe. There is no known concentration of mass large enough or distant enough to account for it. If the pull were coming from something we could see, we would have found it. The gravitational accounting does not balance with anything inside our horizon. Kashlinski's interpretation was direct. Something beyond the observable universe, something we cannot see and cannot reach, is massive enough for its gravitational influence to extend across roughly 14 billion light years and move matter on the largest scales we can measure. A gravitational shadow, cast from beyond the edge of what is visible. In the eternal inflation picture, this has a candidate explanation. Neighboring bubble universes separated from ours by vast distances could have collided with our bubble in the early universe. The collision would not destroy us. It would leave an imprint, a bulk pull, a coherent tug on matter in the direction of the impact. The gravitational presence of something that was briefly, enormously near. Then the data shifted. The dark flow was disputed. Later analyses using data from the Planck satellite produced contradictory results. Some teams found no statistically significant bulk flow at the scale Kashlinski described. The observations are real. The question is whether they mean what Kashlinski proposed, or whether they are a measurement artifact, a systematic bias in the data. The dark flow is currently neither confirmed nor ruled out. It sits in a kind of scientific suspension. The signal exists. Its explanation does not yet. And then there is the second thing the sky says. The cosmic microwave background is the oldest light in the universe. It was emitted 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and light to travel freely for the first time. It fills the entire sky. It is extraordinarily uniform, a near-perfect thermal glow at roughly 2.7 degrees above absolute zero. Identical in every direction to within 1 part in 100,000. That uniformity was already covered. What was not covered is what happens when you look closely at a specific region of the southern sky. There is a patch, several degrees across, which on the scale of the CMB is a significant region. It is colder than its surroundings, not by much in absolute terms, but by enough to matter statistically. The probability of a region that cold appearing by chance, under the standard cosmological model, is less than 1%. This is the cold spot. Two candidate explanations exist. The first is a supervoid, an unusually empty region of space along our line of sight. When photons travel through a region with less mass than average, they lose a small amount of energy passing through the gravitational potential of that void. Some evidence for a void in that direction has been found, but the void that has been identified is not empty enough, not large enough, to fully account for the deficit. The supervoid explanation is partial at best. The second candidate is a collision with another bubble universe. In eternal inflation, bubble universes do not only form, they can intersect. When two expanding bubbles in the inflationary foam grow large enough and close enough, they can make contact. The collision does not merge the universes. It creates a disturbance at the boundary, a circular scar in the cosmic microwave background of each bubble, unusually cold or unusually hot depending on the geometry of the impact, with a characteristic temperature profile that follows the physics of the collision. The cold spot is roughly circular. Its temperature profile is consistent with what a bubble collision would predict. Not vaguely consistent, specifically consistent, in shape and in the gradient of the temperature across the patch. In 2015, physicists Stephen Feeney and Matthew Johnson, working with colleagues at University College London, did something more systematic. They worked out formally what bubble collision signatures should look like in the CMB. They identified the mathematical fingerprint, the shape, the symmetry, the statistical properties. Then, they searched the full CMB data for features matching that fingerprint. They found 4 candidate spots. The cold spot was among them. So were 3 others, distributed across the sky, each with the circular geometry and statistical properties that a bubble collision model would predict. The statistical significance of the 4 candidates was not overwhelming. It was not the kind of result that ends debates, but it was not noise either. 4 spots, the right shape, the right properties, found by a systematic search, not by looking until something appeared. What the evidence shows is specific, not that other universes exist, not that we have proof of a collision, but that the sky contains anomalies which the standard model struggles to explain, and that those anomalies match, with notable precision, what the physics of bubble collisions would predict. The data does not yet decide. It leans, faintly, but in a direction. 2 anomalies, both real observations, both disputed or incomplete in their explanations, both pointing, if they point anywhere, toward the same place the equations have been pointing all along. The sky has not answered the question, but it has not been silent either. But the sky is only one layer of evidence. And the evidence in the sky, however suggestive, is looking outward. What we have not yet done is look inward, all the way inward, past the bubble universes, past the quantum branches, past the string landscape and its 10 to the 500 configurations, past even the ordinary assumption that the 3 dimensions we move through are the fundamental level of reality. Because here is where the deepest question lives. Not whether there are other universes, but whether the architecture of this one is what we think it is. In 1997, physicist Juan Maldacena published a paper. It became the most cited paper in the history of theoretical physics. That is not a casual claim. Thousands of papers are published every year. Most are forgotten within a decade. Maldacena's paper has been cited by other researchers more times than any work in the entire history of the field. Something in it struck everyone who read it as profound in a specific, structural way. What he showed was this. A theory of gravity operating in a 3-dimensional space is mathematically equivalent to a quantum field theory without gravity operating on the 2-dimensional boundary of that space. Not analogous, not approximately similar. Exactly equivalent. The same equations, the same predictions, the same physics, described completely by either description. The technical name for this correspondence is the ADS-CFT correspondence. ADS stands for anti-d Sitter space, a particular mathematical structure for spacetime. CFT stands for conformal field theory, the 2-dimensional quantum theory on the boundary. The names are not important. What is important is the implication. Every physical event in the 3-dimensional interior can be completely described by the 2-dimensional theory on its surface. The interior, with all its depth and volume and gravitational structure, is not adding any information beyond what the boundary already encodes. Nothing is lost in translation. Nothing is hidden in the 3rd dimension that the 2-dimensional theory cannot already account for. The volume is redundant. Think about what that means. The world you move through, the depth you perceive between objects, the 3-dimensionality of every room and landscape and body may not be fundamental. It may be emergent, a projection, an encoding from a 2-dimensional surface rendered into apparent space the way a holographic image emerges from a flat plate. The screen in this picture is more real than the movie. This is the holographic principle. The universe stores information not in volume, but on surface area. The information content of any region of space is proportional to its surface area, not its volume. This is not metaphor. It is not analogy. It is what you get when you take general relativity and quantum mechanics seriously and follow the mathematics to where it leads. The math says, the boundary holds everything. Something else was happening. If our 3-dimensional universe is a holographic projection of a lower dimensional quantum system, Then what are other universes? The boundary theory does not necessarily produce only one bulk geometry. A single two-dimensional quantum system, a single boundary, might support many different three-dimensional solutions emerging from it. Different spacetimes, different geometries, different physical interiors, all described by the same underlying surface. In this picture, other universes are not somewhere else. They are not separated by vast distances or unreachable by the speed of light. They are other projections of the same substrate. The boundary is the thing. The three-dimensional worlds emerging from it are what change. This is the most speculative of the multiverse pictures, but it is not speculation in the loose, philosophical sense. The mathematics is rigorous. The correspondence Maldacena proved is not approximate. It is exact in the setting where it has been established. Whether that setting extends to our actual cosmology is an open question, but the mathematics that permits it does not have to be forced. It already exists. Wait, there is something deeper still. In 2013, Maldacena, working together with Leonard Susskind, proposed what they called the ER equals EPR conjecture. Two abbreviations. ER refers to the Einstein-Rosen bridge, the technical name for a wormhole, a connection through space-time. EPR refers to Einstein, Podolsky, and Rosen, the three physicists who first formally described quantum entanglement. The conjecture says they are the same thing. Quantum entanglement is the property by which two particles, once they have interacted, remain correlated across any distance. Measure one and you instantly know something about the other, regardless of the space between them. This has been experimentally confirmed. It does not allow faster-than-light communication, but the correlation is real and it persists. The standard view was that entanglement was a kind of bookkeeping, a statistical correlation between remote objects. Nothing physical connecting them, just a shared history recorded in a quantum state. The ER equals EPR conjecture says the standard view is wrong, not incomplete, wrong in its framing. What entanglement actually is, the conjecture proposes, is a microscopic wormhole, a tiny bridge through space-time, an Einstein-Rosen bridge connecting the two particles at the level of space itself. The correlation is not just bookkeeping, it is a physical connection. The fabric of space in this picture is woven from entanglement. Every pair of entangled particles is a thread. Space is what you get when you weave enough of those threads together. Think of it this way. Take 2 points in space and imagine the space between them as built from the quantum connections linking the particles at each point to particles elsewhere. Remove the entanglement, and the space dissolves. Add entanglement between distant regions and space stitches itself together across them. Space is not the container that holds quantum objects. Space is what quantum entanglement produces. This is still a conjecture. It is not proven the way Maldacena's 1997 correspondence is proven, but it has passed several non-trivial consistency tests and is taken seriously by researchers in quantum gravity as a genuine proposal about the structure of reality. And if it is right, the consequences do not stop at space. If space-time is emergent from entanglement, and entanglement is a quantum phenomenon, then space-time itself is a quantum object. And quantum objects exist in superpositions. A particle has no definite position before measurement. It occupies all its possible positions at once, weighted by probability. If space-time is built from quantum entanglement the same way a particle's position is built from quantum states, then space-time itself has no definite geometry until something selects one. At the scale of a single region, this might produce small fluctuations. But at cosmic scale, something more radical follows. The wave function of the entire cosmos, the complete quantum state of the universe taken as a whole, may exist in a superposition. Not a superposition of particle positions. A superposition of geometries, multiple spacetimes, multiple spatial configurations, multiple universes encoded simultaneously in the quantum state of the underlying system. This is a further route to the quantum multiverse, not through branching at the moment of measurement, though that door is still open. through the deeper fact that the space-time those branches inhabit may itself be a quantum object, and quantum objects in superposition are real in all their states. What we are left with, after all four doors and this substrate beneath them, is a layered picture. Inflation opened the first door and produced an endless foam of bubble universes with varying constants. Quantum mechanics opened the second door and produced a branching tree of outcomes, each one real. String theory opened the third door and provided the menu of possible physics that could populate those bubbles. The simulation argument opened the fourth door and found that a computational substrate broad enough to run our universe might run others. And now, beneath all four, a fifth layer, the possibility that our three-dimensional universe is itself a projection from a two-dimensional boundary, that space is woven from entanglement, and that the wave function of the entire cosmos may be in superposition over many geometries at once. The four doors were each discovered independently. Each led to the same room. The holographic picture is something stranger still. It does not add another room. It asks whether the building itself is what you thought it was. That question does not have a final answer yet, but the mathematics that raised it is the most precisely developed framework in theoretical physics. And that means the question is not going away. But before we go further, we should pause. Because the most honest version of this argument has to take the critics seriously. And there are serious critics. The most common objection is this: if other universes cannot be observed, cannot be reached, and produce no measurable effect on ours, then the multiverse makes no testable predictions. A theory with no testable predictions is not science. It is metaphysics. The distinction matters. Physics advances by producing claims that could, in principle, be wrong. The multiverse, on this reading, cannot be wrong because no observation could ever contradict it. This is not a fringe complaint. It is raised by working physicists whose work on other problems is impeccable. And the objection has real teeth. The level 1 multiverse, the idea that space extends infinitely beyond our observable horizon and contains other regions with the same laws but different histories, is unfalsifiable by definition. We cannot see past the horizon. We never will. The level 2 multiverse, the bubble universes produced by eternal inflation, is also generally unfalsifiable. Each bubble is causally isolated from every other. The many worlds branches are unobservable from each other by construction. If you are in one branch, the other branches produce no signal you could ever detect. Here is the defender's reply. Science routinely accepts entities that cannot be directly observed, provided they are necessary outputs of well-confirmed theories. Quarks cannot be directly observed. No experiment has ever isolated a free quark. They are inferred from the behavior of particles in high-energy collisions. Black hole interiors cannot be observed. No signal escapes from beyond the event horizon. Dark matter has never been directly detected. Dark energy is inferred from the expansion rate of the universe, not seen. None of these absences have led physicists to abandon the theories that produce them. The same logic applies here. Inflation is confirmed by the cosmic microwave background. WMAP in 2003 and Planck in 2013 both found the precise quantum fluctuation patterns inflation predicted. That is not disputed. If you take inflation seriously, which the data demands, eternal inflation follows. If eternal inflation proceeds, bubble universes form. The unobservability of those bubbles is not a metaphysical barrier. It is a consequence of finite light speed and the distances involved. The bubbles are out of reach. They are not outside nature. That answers the first objection. But there is a deeper one. The string landscape contains something in the range of 10 to the power of 500 possible configurations of physical law. We have covered that number before, and the scale of it remains staggering. Now, combine that with the anthropic principle. We observe the constants we observe because we exist in a universe that permits our existence. Put those two things together and the question, why these constants, answers itself. Of course the constants permit life. We would not be here to ask if they did not. This is an explanation of a kind, but it is not the kind physics was built to produce. It cannot be refined. It cannot be improved. It cannot be tested against an alternative. Any set of constants, however improbable on any prior distribution, becomes explainable after the fact by noting that we are here to observe them. The anthropic principle, taken far enough, is a machine for eliminating the need to explain anything at all. Physicists Lee Smolin and Peter Woit have pressed this point hard. Their argument is that the string landscape is not a discovery. It is a symptom. A theory that produces 10 to the power of 500 solutions has, in their view, lost contact with the standards of science. String theory should be abandoned, or at least radically revised, not celebrated for the vastness of its solution space. Smolin proposed an alternative. He called it cosmological natural selection. The idea is that universes reproduce through black holes. Each black hole spawns a new universe with slightly altered physical constants. Universes that produce more black holes produce more offspring universes. Over many generations, the constants drift toward values that maximize black hole production. Our constants, on this view, are not anthropically selected, but evolutionarily selected. Cosmological natural selection has the virtue of being at least partially falsifiable. If the constants in our universe were shifted slightly, would the result be more or fewer black holes? Some tests can be sketched, but the theory has not gained wide acceptance. Its mechanism remains speculative, and the underlying assumptions about universe reproduction through black holes are not yet grounded in well-confirmed physics the way inflation is. So here is the honest summary. The multiverse is not proven. The evidence for it is theoretical, not observational, with the marginal exception of the CMB anomalies already discussed. The testability objections are real and have not been fully answered. The anthropic principle, applied to the landscape, raises genuine concerns about whether physics has handed itself a blank check. But the multiverse is not arbitrary. It is not invented to make the equations pretty or to rescue a failing framework. It is the output of the most successful physical theories we have, followed to their logical conclusions. Discomfort is not a scientific argument. Discomfort is not data. And here is where the argument takes a structural turn. In 2019, the Event Horizon Telescope released the first direct image of a black hole. It showed the glowing ring of superheated gas around the shadow of the black hole at the center of galaxy M87. The image was clear. The ring was exactly where general relativity said it would be. Nobody watching that announcement questioned whether black holes were real. The theory had earned that confidence over 100 years of accumulated indirect evidence. The multiverse is not at that stage. There is no image. There may never be one. But the theoretical case has been building for 60 years, and it now rests on multiple independent pillars. Inflation, developed to solve the horizon and flatness problems, produces a multiverse of bubble universes. Quantum mechanics, the most precisely tested theory in the history of science, produces a branching structure of parallel outcomes when its equations are taken literally. String theory, developed to unify quantum mechanics and gravity, produces a landscape of 10 to the power of 500 possible sets of physical law. The holographic principle and the ER-EPR conjecture suggest space-time itself may be emergent from a lower dimensional substrate that could project multiple geometries at once. These pillars were not designed to agree. Each was built to solve a different problem. None of them were aimed at the multiverse. The convergence was not engineered. That matters. Guth wanted to fix the horizon problem. The equations gave him eternal inflation. Everett wanted to remove an unexplained patch from quantum mechanics. The equations gave him infinite branches. String theorists wanted a unique theory of everything. The equations gave them 10 to the power of 500 solutions. In each case, the physics led somewhere no one planned to go. That is the signature of a discovery, not a choice. Scientists who set out to find something and find it have confirmed their expectations. Scientists who set out to find something and find something entirely different, repeatedly, across independent frameworks, across decades, across the most rigorous mathematics available, have found something. We do not yet know what. The answer may come, or it may not. But the building has been under construction for 60 years, and the foundations are not going anywhere. Let's suppose, for a moment, that this picture is right, not as a thought experiment, not as a philosophical exercise, but as a serious possibility that follows from the equations. What does it actually change? Start with the level 2 multiverse. In that picture, each bubble universe that eternal inflation produces can settle into different physical constants, different proton mass, different strength of electromagnetism, different speed of light, different cosmological constant. We have always treated these values as laws, universal, fixed, the bedrock of reality. But here is what that picture actually implies. They are not laws at all. They are local conditions. What we call fundamental physics is, from the perspective of the whole, more like regional geography. The rules we discover in our laboratories are not the rules of reality. They are the rules of our bubble. They are the climate of our particular patch. A physicist doing experiments in a different bubble, under different constants, would measure a completely different set of values. And they would call those values the laws of physics, because from inside any single bubble, there is no way to see the boundary, no way to know that what feels universal is merely local. The feeling of universality is built into the structure of being embedded in one place. Think about what that means for the scientific project. Everything we have ever measured, every particle accelerator run, every telescope observation, every controlled experiment in every laboratory in human history has been mapping one region, one patch of a larger terrain we cannot see. The map is accurate. It is the best map ever made. It is just not the map of the whole territory. That is the level 2 implication. Constants as geography, laws as local custom. But the many worlds picture carries a different set of implications, and they reach closer to home. In many worlds, the branching is continuous, trillions of times per second, in every cubic centimeter of matter. Every quantum event that could go more than one way goes every way, in branches that immediately diverge and cannot interact. And every choice a human being makes is, at the physical level, a quantum process unfolding in a quantum brain, which means every choice also branches. The question shifts. It is no longer, what will I choose? That framing assumes a single thread of identity moving forward through one future. The question becomes, which version of me do I become? There is no version who does not exist. There is a branch where you turned left, and a branch where you turned right. Probability in this picture is not the chance of an outcome. It is the measure of which branch the pattern you call yourself lands in. You do not avoid outcomes. You bifurcate into them. But here's where it gets strange. Under many worlds, death is also a branching event, not a singular endpoint, not the place where the thread of identity simply stops. In some branches, a person survives what kills them elsewhere. The bullet misses by a fraction of an inch. The car veers the other way. The diagnosis arrives a year earlier. In those branches, that version of the person continues. In the branches where it does not miss, where the car does not veer, where the diagnosis comes too late, that version does not. Every death is a partition. Some branches carry the pattern forward, others do not. This is not immortality. It would be a mistake to call it that. It is something stranger and less comfortable. It is permanent dispersal. The you that exists right now, reading this, is already many versions of itself in many branches. Death does not gather all those versions and extinguish them at once. It separates them. It partitions the probability weight. The branches where you survive are real. The branches where you do not are also real. The word immortality implies a self that persists intact. Many worlds offers no such thing. What it offers instead is a different conception of what ending means. Some people find that deeply unsettling. Others find it quietly freeing. The discomfort, if it comes, is not evidence against the picture. It is just the feeling of a very old assumption being set down. And then there is the holographic picture, which carries its own kind of strangeness. If the holographic principle is correct, the three-dimensional space you occupy right now is not the bottom of reality. It is a rendering. The actual substrate is a two-dimensional quantum system. A surface, a boundary. That surface encodes all the information your three-dimensional experience contains. The depth you perceive when you look across a room, the volume of your body in space, the distance between objects, all of it is projected from a lower dimensional layer the way a lens takes a flat pattern and throws it into apparent space. The three dimensions are real in the sense that the description is accurate. The chair is where the chair is. The distances are what they are, but depth and volume are not the foundation. They emerge from a foundation that does not itself have those properties. We are not as solid as we feel. That is not a poetic observation. It is, under holography, a literal one. The solidity, the three-dimensionality, the felt sense of spatial depth, these are outputs of a process happening on a surface. The map is more real than the territory it projects. None of this is emotionally comfortable in the way that very old certainties being revised are never comfortable. But comfort is not what physics is for. Physics is for describing what is actually there, as accurately as the mathematics and the measurements allow. Whether the description is reassuring has never been a criterion. Copernicus was not reassuring. Darwin was not reassuring. The discovery that space is curved by mass was not reassuring. And yet each time, the discomfort faded, and the picture it left behind was more accurate than the one it replaced. The four multiverse pictures, taken together, do not just add rooms to the house. They revise what the walls are made of. Constants are local. Choices branch. Death is a partition. Three-dimensional space is a projection. And underneath all of it, a mathematical substrate that does not owe its shape to the experience of the beings it contains. That revision is still in progress. The pictures are not all confirmed, but they are not guesses either. They are the logical conclusions of some of the most carefully verified frameworks in the history of science. And what they collectively suggest about the nature of reality is still only beginning to be absorbed. The deepest questions have not yet been answered, but the shape of the questions has changed. And that alone is a different kind of knowing. While those implications were still settling, the physicists were not waiting. The multiverse is routinely described as untestable. A beautiful idea perhaps, but one that lives permanently outside the reach of instruments. That description is wrong. Not partially wrong. Specifically wrong in ways that matter right now. The Simons Observatory in Chile is operational. The CMB-S4 experiment, a next-generation network of telescopes designed to measure the cosmic microwave background, with a precision roughly 50 times better than the Planck satellite, is in development. That level of sensitivity is not incremental. It is the difference between a blurry photograph and a high-resolution image of the same scene. And what these instruments are looking for, among other things, are bubble collision signatures. Those 4 candidate spots that Feeney and Johnson identified in the Planck data will either sharpen into statistically significant signals or dissolve into noise, not in some distant future, within the current decade. The answer to whether the CMB carries physical imprints of other universes is coming, while some of the physicists who first asked the question are still alive to see it. But the CMB is only one line of inquiry. Here is where the picture becomes genuinely surprising. Quantum mechanics has its own experimental frontier bearing directly on the multiverse. The central question is whether quantum superposition, the capacity of a system to exist in multiple states simultaneously, has any natural cutoff. Many worlds says it does not. The wave function does not collapse at any scale. Superposition persists in atoms, in molecules, in living cells, in detectors, in physicists. The branching is universal and absolute. If that is true, then quantum coherence, the maintenance of superposition before decoherence scrambles it, should in principle be achievable in progressively larger objects. Not just electrons, not just individual atoms, molecules with thousands of atoms, then more still. Experiments are now approaching the mesoscale, the regime between the quantum and classical worlds where no one is yet certain what the rules are. Objects large enough to see under a microscope are being coaxed into superposition states in laboratories. If at some scale, coherence breaks down irreversibly, if collapse turns out to be a real physical process rather than a bookkeeping shortcut, many worlds is ruled out. Not weakened, ruled out. And if no such cutoff is found, if coherence scales upward without limit as many worlds predicts, the case for branching becomes harder to dismiss. The experiments will not produce a photograph of another branch. They will do something more subtle and in some ways more powerful. They will constrain the physics. They will tell us whether the wave function collapses, and if it does not, the universe that Everett described in 1957 becomes the universe we are being forced to accept. String theory has its own empirical frontier, though a more frustrating one. The absence of supersymmetric particles at the Large Hadron Collider has disappointed a generation of theorists. The LHC reached energies where many leading string theory models predicted supersymmetry should appear. It did not appear. But this is not fatal. String theory does not predict precisely where supersymmetric particles should emerge. The theory's landscape of possible configurations does not converge on a single clean prediction that can be knocked over by a single result. What the LHC absence does is narrow the territory. Future colliders at higher energies will narrow it further. Either supersymmetry will appear, or it will be ruled out at scales that constrain the landscape significantly. Meanwhile, the mathematical framework of ADS CFT, the holographic correspondence between gravity in 3 dimensions and quantum field theory on a 2-dimensional boundary, continues to produce testable predictions about information structure in space-time. Holographic entropy calculations are being checked. Quantum error correction in quantum gravity is being developed and tested. These are not direct multiverse tests. They are tests of the foundational framework that the holographic multiverse depends on. If the framework fails, the house comes down. If it holds under increasingly precise scrutiny, the picture it supports becomes harder to set aside. So 4 distinct experimental programs, the CMB search for collision signatures, mesoscale quantum coherence experiments, the LHC and its successors, and the ongoing work in quantum gravity are all bearing on the question from different directions. Each one is constraining a different door, and the honest truth is that none of them will produce a photograph of another universe. The multiverse may never be confirmed the way the Higgs boson was confirmed, with a sharp signal against a flat background, a date, a press conference, a single moment when the question closed. But consider what that comparison actually requires. The Higgs boson was proposed in 1964. It was confirmed in 2012. 48 years of theory earning confidence through accumulated evidence, through precision measurements of everything around it, through the standard model passing every test put to it, until the confirmation, when it arrived, landed not as a surprise but as an inevitability. Quarks were proposed in 1964 as well. They have never been isolated. No one has ever held a quark. They are inferred from the behavior of high-energy particle collisions, and every physicist treats them as real. Gravitational waves were predicted by Einstein in 1916. They were confirmed 99 years later. Black holes were a mathematical solution before they were an observed object. For a century, they existed in the equations. This is how physics works at its frontier. Confirmation is not always a photograph. Sometimes, it is the accumulated weight of every other test pointing in the same direction, until the conclusion becomes the only one the evidence supports. And underneath all of it, even once the experimental programs have run and the data has come in, a question remains that physics is not equipped to fully answer. The multiverse, in any of its forms, does not dissolve the deepest problem. It only relocates it. The question is not why this universe has the constants it has. Frameworks exist for that now. The question is why there is anything at all. Why is there a wave function? Not what the wave function describes, but what it is, and within what it is evolving. Why is there an inflaton field capable of generating eternal inflation? What produced the conditions that allowed inflation to begin? If the string landscape contains 10 to the power of 500 configurations, what contains the landscape? If the holographic boundary encodes three-dimensional space, what is the boundary a boundary of? Each answer generates a larger container. Each larger container requires its own explanation. Eternal inflation explains our constants, but requires an inflaton field. The inflaton field requires a quantum framework. The quantum framework requires a wave function. The wave function is not self-explaining. Push in any direction, and you arrive at another door with no key. This is not a failure of the multiverse, it is a feature of how knowledge expands. Physics has been doing this for centuries. Matter was continuous until it was atomic. Atoms were fundamental until they had nuclei. Nuclei were fundamental until they had quarks. Each level of explanation opened a deeper level of structure. There is no reason to believe the current moment is different. Every reason to believe it is not. Think about what that pattern actually describes. We used to place Earth at the center of everything. Then the solar system, then the galaxy, then the observable universe. Each time, the truth was larger than the frame we had built. Each time, the new frame was stranger and less centered on us than the one it replaced. The multiverse is the next step in that sequence. Not the last one, the next one. The universe we know is almost certainly a small, local structure inside something vastly larger that we are only beginning to outline. Physics now says the multiverse exists, not with certainty, not with a photograph, but with the weight of multiple independent lines of evidence, drawn from theories tested to extraordinary precision, all pointing in the same direction. The question is no longer whether the multiverse is serious science. The question is which version of it turns out to be right. Eternal inflation producing bubble universes. Quantum mechanics generating branching branches. String theory providing the menu of possible constants. Holographic geometry encoding space-time from a lower dimensional surface. Some combination of these. Something we have not yet conceived. The answer is coming. Maybe not in our lifetimes. The experiments will take time. The theories will need refinement. The picture will sharpen slowly, the way all pictures at the frontier of physics have sharpened. Incrementally and then suddenly, through accumulation and then through the moment when the evidence tips. And when it does, it will not be the last time we are surprised by how large everything turned out to be. It will be the next time. That is the pattern. That is what the history of this science, from Copernicus to Darwin to Einstein to Everett, has been trying to tell us all along. The universe is larger than we thought. It has always been larger than we thought. And the thinking, even now, has not caught up.